variation with time t of the sinusoidal current I in a resistor of resistance 450 ohm is shown in figure 11.1. Use data from figure 11.1 to determine for the time t equal to 0 to t equal to 30 millisecond the frequency of the current. So you want to find the frequency of the current, so you have to find the period. Okay, to find the period, let's take maximum to maximum. Here to here. So maximum 2.5. Here maximum 17.5. Okay, so the period 17.5 minus 2.5, 15 millisecond. The frequency 1 over period. So you get 66.7 hertz. Okay, or round off to 67 hertz. Okay, the mean current. Mean current, be careful. We have 3 type of current, Okay, right at the side here, we have peak current. Peak current is I naught, the maximum. For this case, I naught is this value, 0.75. Okay, that is peak current. We have root mean square current. Root mean square current is IRMS equal to I naught over square root 2. We have mean current. Mean current is I maximum plus I minimum divided by 2. Like finding the average, So for mean current here, you take maximum 0.75 plus negative 0.75 divide by 2. Then you get 0, You get 0. 0 ampere. Maximum plus minimum, then divide by 2. So end up with 0. Mean current. Root mean square current. Okay. So the peak value is 0.75. This is I naught. So if I naught is 0.75, then we use formula to find the root mean square. Root mean square is I naught over sub 2, 0.75 over sub 2. So we get 0.53 ampere. Okay. So after that, the energy dissipated by the resistor. Okay, so energy is power multiplied with time. And if the current passes through the resistor, so we have to use I square R to represent the power. And the I, right, cannot be any I, There are 3 types of I so far. So we have to use the root mean square I. Root mean square current. So which is 0.75 over square root 2 just now. Then you square it. Multiply with the resistance. So the resistance is here, 450 ohm. multiply with the time. So that take a total of 30 milliseconds. So we want to find out the energy dissipated by the resistor in the whole process. So which is 30 milliseconds. So then we get 3.80 joule. Okay, so this is considered quite direct. Okay, an ideal transformer is shown in figure 9.1. Explain why the core is made of iron. Okay, so to increase magnetic flux linkage. If you're wondering when should you use magnetic flux linkage, so when the magnetic field cut the conductor and induce EMF, and then you have to use magnetic flux linkage. Okay, so it is used when EMF is induced. To increase magnetic flux linkage with the secondary coil. Okay, part 2. Why an electromotive force EMF is not induced at the output when a constant direct voltage is at the input. So they are using direct voltage, not alternating voltage, direct voltage. And direct voltage is a constant value. So EMF is induced only when magnetic flux in core or coil is changing. So if you are using constant direct voltage, there is no change in the magnetic flux. Then no EMF is induced. Okay, so of course, like what I said, when you turn on the induce for a short period of time, then after that, no more value already, becomes zero already. Okay, so we assume that is not induced. Okay, so we have to use alternating current or alternating voltage. Now they use an alternating voltage of peak value 150 volt. So I label first. This is V naught. It's applied across the 100 or 1200 turns of the primary coil. This is the VP. VP, VP naught. This is NP. The variation with time t of the EMF induced across the secondary coil is shown in figure 9.2. Okay, so they give us the graph, and be careful with the words that they use. The variation with time t of the EMF E induced. EMF induced is Vs. Vs, the secondary V. Okay, now let's see the other side. Use data from figure 9.2 to calculate the number of turns of the secondary coil. So we use this formula. Ns over Np equal to Vs over Vp. So Ns unknown, Np 1200, Vs and Vp you may be wondering, should I use root mean square or should I use peak? So I will tell you, both will be fine. So if your information available here is peak voltage, then your Vs have to use peak voltage also. Peak voltage, okay. So which is peak voltage. $52. $52, the peak voltage. Okay, so for this formula only, you can use peak voltage or root mean square voltage. It's okay. But if it's power, right, like mean power, then you must use root mean square voltage and root mean square current. If it's peak power, then you can use peak voltage and peak current. But this one flexible. So I write here first. If you are finding the mean power, then you can use V root mean square, I root mean square. When you are finding the peak power or the maximum power, then you V naught I naught. For this one, V naught I naught or V root mean square will be just, I mean you can use peak voltage or use root mean square voltage. Okay, so since the information given is peak, so I will just use peak. Then you get an S, 416 turns. Okay, now part 2. State one time when the magnetic flux linking the secondary coil is a maximum. Magnetic flux linking, the phi. Okay, so when is the phi be maximum? Okay, let's look at the graph here. This is not the graph of phi, this is the graph of Vs. Then how is the graph of phi? Let's think about it. Based on what we learned just now, you have to memorize the phase difference. Okay, so I quickly put it here. From our information just now, Vp Vs has 90-degree phase difference with Ip Is or phi. This set, any of this, has a phase difference of 90 degree with any of this. Okay, so they give Vs. They give you Vs. Then now they give you phi. Oh, no, now the question asks for phi. So there is a phase difference of 90 degree. Okay, so we should expect a phase difference of 90 degree. So it will be like, we'll start later. Let's start here. Then let's start. And here is 0, here will be maximum then. The value we don't know lah. No? We don't know how tall it go. We just know this is the graph of phi. What value don't know lah. Of course this scale also not suitable. But we just know in general the shape is like that. Okay, so when they reach minimum, then here they will reach 0. There is a delay of 90 degree. So likewise here, what value don't know. But that value not really important one, This value is what value we don't know because this is the graph of phi. This is the graph of phi. the question is asking for the time when the magnetic flux linking the secondary coil is maximum. So it is maximum at here, okay, at here, 75, no, 7.5 milliseconds, okay, 7.5 milliseconds. This is acceptable. If you put other value, like for example, okay, hold on, if you put other value like 0 millisecond, the accept also, 0 millisecond, the accept, or even if you put 7.5 millisecond or 15 millisecond, the accept, 15.0 millisecond or 22.5 millisecond, the accept also. Okay, so for my case, 7.5. Of course, if the phase difference is 90 degree, right? So maybe your graph is like this, you know. Maybe your graph is like this, like the green one. That is phase difference of 90 degree also, you know. So for this case, right, if your graph is like this with a phase difference of 90 degree in the green color way, the maximum happen at 0 millisecond and the maximum happen at 15 millisecond. Okay, so it happened there, you know. If you follow the red graph, which have a phase difference with the black color graph also at by 90 degree. So then you can see maximum can happen at 7.5, can also happen at 22.5. So that's why quite many choices. So if you follow red graph, maximum is 7.5, 22.5. If you follow green graph, maximum at 0 and 15. So they have phase difference of 90 degree from the black color graph. Okay, so now let's see the next one, part C. A resistor is connected between the output terminal of the secondary coil. The mean power, I see they use mean power. So just now I already mentioned mean power, VRMS times IRMS. The mean power dissipated. If mean power dissipated, you don't use this. Yeah, you don't use this. You use the one involved resistance. Involved resistance. Okay, so what are the other options other than this? So we have mean power equal to I square R or V over R. So if it involves power loss or power dissipated, so using these two will be better than this one. Must involve the resistance that causes the power loss. Okay, so the mean power dissipated in the resistor is 1.2 volt. It may be assumed that the varying voltage across the resistor is equal to the varying EMF E shown in figure 9.2. That means we can use the graph in part B just now, figure 9.2. Okay, we can use this graph for our calculation. So this graph gives us V naught, which is 52. 52. So let's use this formula, the V RMS square over R. So I write down the formula first. P mean equal to V RMS square over R. RMS is V naught square over Z2 over R. Okay, now we substitute with value. Mean power 1.2, V naught 52, 52 square over Z2 divided by R, and R equal to 1130. Okay, part 2. On figure 9.3, sketch the variations with time t of the power P dissipated in the resistor for t equal to 0 to t equal to 22.5. Okay, so as you can see, the power dissipated is affected by the root mean square voltage, or the V naught square. V naught square. Okay, so if you look at this graph again, the black color graph is the output voltage. So the output voltage will affect the mean power. Okay, will affect the mean power. But the thing is, there is a square there. If there is a square, right, that means they won't become negative. Like this one, okay lah, this one positive, right? When it's negative, right, imagine you square it, as in the formula here, you square it. When it's negative 52, right, so it will become positive something, right, you know, so it will come out already. Okay, so positive of course remain it's just that you square it and it become bigger. Okay, then you divide by something else Okay, then after that this one come out also, then this one come out again, so we should expect something like this. And the what value should we take? We have value here, you know, 0, 1.0, 2.0, 3.0. Okay, so if you look at this formula, right, together with what I mentioned also, let's see. There is a peak power that is going to happen also, you know, where imagine P peak equal to V naught square over R. So this one should be reasonable here. When the voltage is maximum, as in here, then the power should be maximum, because you square it and then you divide by R, right? So it should be maximum also. Okay, let's see what value is that. 52 square over 1130. So it's roughly about 2.4 volt. Okay, so that means, imagine based on the formula, based on this formula, V naught square over R. So when it is 0, then the power should be 0. So we have 0 at here, at 7.5, at 15, at 22.5. Then it reached maximum in the middle at about 2.4. 3 point something middle, okay, 2.4. Okay, and 2.4 again, and 2.4 again. So it's always positive because there's a square there. And we get the graph. Okay, so settle this question. A bridge rectifier contains 4 ideal diodes A, B, C, and D as shown in figure 11.1. The output of the rectifier is connected to a load L of resistance 2.4 kilo ohm. On figure 11.1, mark with the letter P the positive terminal of the load. Positive terminal of the load. Okay, so let's imagine. The current is alternating current because you see a wave here. So let's say if the current come up from here, they reach here, then they cannot go to B, right? Because opposite direction. So they go to A, then they come down, and they come here, and they flow here. Okay, we focus on here, they come out. The current is going up. And then they come here, go back to the source. So after a while, the current may come down. When they reach here, they cannot go to C because it's blocking. So they go here, then come down, come here, and go up again. So the current is always go up, then come here, come up, go back. So we focus on this part. If current is always go up, then the positive terminal is okay. Let's see first. Let's see. Page 11. Okay, it's here. The positive is there. Okay, now settle A. Let's look at B. The variation with time t of the potential difference V across the input to the rectifier is shown in figure 11.2. Okay, so calculate the root mean square current in the load L. Okay, so to calculate the root mean square current, that means we have to count the root mean square I. Root mean square I. Okay, so let's put it here. Our graph gives us V versus T. So we can only do root mean square voltage, which is V0 over Z2. And the V0 is 6 over Z2. 4.24 volt. So we get root mean square voltage, but we don't get root mean square current. So we have to use V equal to IR. V root mean square equal to I root mean square times R to get the I root mean square. So 4.24 equal to I root mean square multiply with the resistance 2.4 kilo ohm. That is 2400. And then we'll get I root mean square 1.77 times 10 minus 3 ampere. Okay, so now let's move on. Part C. The potential difference across the load L is to be smooth using a capacitor. On figure 11.1, draw the symbol for a capacitor connected to produce smoothing. Okay, so you have to remember, capacitor must connect in parallel with the load. Okay, so we draw like this. Okay, so that's the answer. And part 2. The minimum potential difference across the load L with the smoothing capacitor connected is 3.0 volt. On figure 11.2, sketch the variation with time t of the potential difference across the load L. Okay, so minimum is 3.0, and there is a smoothing process that happens. Okay, so that means minimum is 3. Okay, let's magnify it a bit. So let's start from maximum. That means the capacitor is going to discharge and discharge to 3 volt, then they have to charge again. And the other thing is, this is quite tricky also, must be very careful. This graph is the input of the I mean this is the input lah. The voltage here is the input, the potential difference is the input lah. And after that, this input, right, imagine this input after going through the rectifier, so there will become full wave rectification happen. Full wave rectification happen. So first of all, we need to know a graph like this, after full wave rectification, will become like that. Will become like that. Then there is a smoothing also. So the smoothing, right? Like what they said, the smoothing capacitor will make the minimum potential difference to be 3.0 volt. That means, let's say you draw a 3 volt here. Then they will go down until 3 volt, then charge, go down until 3 volt, charge, go down until 3 volt, charge, and go down until 3 volt and charge, and so on. So until 3 volt, they can't go lower anymore. Until 3 volt, then they have to recharge already. Okay, so let's put it here. Okay, so first let's say I draw out the output first with the full wave rectification. It will be like this, and like that. Okay, so after that, there are smoothing also until 3 volt. So let's see, the 3 volt is somewhere in between. Volt. Okay, now let's say I use red color. So when the discharge, it draws straight line. Then the charge, follow the curve. Now when the discharge, straight line. Then follow the curve until maximum. Then draw a straight line to the minimum. Charge, straight line, charge, then straight line. Okay, so the red color graph will be the graph required. So after smoothing, it look like that. So involve two process: rectification first, full wave rectification first, then smoothing.